Okay, this is the homework from 4F, Part 1, but we're about to start the lesson for 4F, Part 2. Okay, describing a binomial distribution. So to graph the binomial distribution with n equals 5 and p equals 0.25. So how in the world would you graph that? So type the possible values of the random variable x into a list, highlight the list, and create the list. Okay, so this is one way of doing it. So let's see if we could do this. Okay, so let's get our calculator out. I'm just going to start with a new document. It's probably a good idea to do every once in a while. Hit the home key, number 1, don't save changes. So we're going to add a list in spreadsheet. So let's call this first list n values. I don't know. Okay, so we're going to say, because n is 5, it could be 0, 1, 2, 3, 4, and 5. Okay, so the second list, we're going to call that probabilities, I guess, or prob. I'm going to put in the equal sign here. So I'm going to do, so it sounds like you can do binom PDF here and just do it that way. So menu, let's see if it lets me do math. Binomial. Rand, that's not what I need. Okay, let me try one more thing here before I give up. Oh, stats, maybe it's in stats. Distributions, binomial PDF, there it is, sorry. Okay, so n is 5, and probability of success is 0.25. And I'm going to leave that one. Do you see where it says optional there? So we're not going to fill it in. We're just going to say okay. And when I press enter, I think it'll fill in all the options there, 0, 1, 2, 3, 4, 5, and it gives you all the probabilities there of those things happening, the likelihood. It's like doing the binomial theorem 5 times or 6 times actually, because it goes 0 through 5. So now we're going to graph that. So I think the histogram. So let's go to the histogram. So go to the statistics page, choose the n values. And remember for this one, if we go to the second choice here, plot properties, and go to add Y summary list, I think that's where we add the probabilities, and it should do a histogram. Let's see if ours looks like theirs. Yeah. Right, so we can see all the likelihoods of those happening. You can see that if there's a 0.25 chance of something happening, you know, 1s and 2s, these are real popular answers there because out of 5, you're getting 25% typically. So it makes sense that the peak is somewhere around 2-ish there, and so good. If account X has a binomial distribution, so this formula is somewhat intuitive, actually, weirdly, but it's really nice to know. And it's on the formula sheet, and you got it. So the mean of a binomial distribution is just n times p. So that last one, it would just be 5 times 0.25. So we would expect the mean to be 1.25, because that's what 5 times 0.25 is. And by the way, the mean was, it looked like somewhere around 1.25. It was between 1 and 2 there on the histogram, so that looks about right. It is on the formula sheet, which is nice. Standard deviation is square root of n times p times the third thing. I call this Q, but it's probably a failure or the complement of the probability of success. So if success was 0.8, this would be 0.2. So it's just the complement of that. So that's standard deviation for binomials only. So it's a special formula for binomials. They only work for binomials. These are not for everything else. Okay, so go back to the pop quiz activity. They guess an answer. So in terms of the correct answer, okay, so we already talked about that. So here's a histogram of the probabilities. You can see that 2 is pretty likely. Let's see why that would be. So what is the mean going to be for this? So mean is just n times p, 10 times 0.2. If you normally are going to get about 20% of the questions right, there's 5 answer choices, you're going A through E, it's just kind of random. And so you go, well, I got a 20% chance. So if there's 10 questions, 10 times 0.2, to me that's intuitive. That's going to be 2. It makes sense that the tallest bar is at 2 there when you do the histogram. It also makes sense it might be skewed right a little bit there because you might get lucky and get more than that, but it's hard to get much less than that. 0 would be the smallest you go there, so I think it's going to be a little bit skewed right in generally. For this kind of, there could be an outlier there on the right, that kind of thing, just because you might get a 9 or 10 or something when you do simulation. Describe the shape. So it's definitely skewed to the right with a peak at 2. Calculate, interpret the mean. So the mean we didn't interpret. So the mean is 10 times 0.2, which is 2. So the average amount of correct answers you would get on this pop quiz would be 2 if you did many, many trials. So let's see what it says. If many, many students took the pop quiz, we'd expect them to get 2 answers correct on average. Good. Calculate, interpret the standard deviation. Remember, the formula is square root of n times p times q. So in this case, it'd be square root of 10 times 0.2, which is 2, times 0.8, and then the square root of that. So you type into your calculator, you get 1.265. So it says interpret, so that means if many students took the pop quiz, their scores would typically vary from the mean by about 1.265 correct answers. And you can see they're about 1 or 2 away from the mean there in general. So the 10% condition, this relates to independence. So, sometimes it's hard to like say, well, are these things independent or not? And sometimes it's obvious and sometimes it wasn't. Well, there's actually kind of a test you can do. So it's a condition or a test we do to see if something's independent in this setting. So if we plug in n, again, n for that problem was, n was 10. So if 10 is less than 0.10 times capital N. Capital N is the population of size capital N, right? So that's the population entirely. So if we sample less than 10% of the population, that's considered independent here. That's okay. So if there were, I don't know, lots and lots of M&Ms produced, and we take one bag and it's less than 10% of all the M&Ms produced, we're okay, right? But if we, there are some things that are just very limited supply. I'm trying to think of something that would be, but let's just say there were 10 Teslas in all of Memphis. There's actually a lot more than that, but let's just say there were, and I sampled 3 of them. Well, that's not going to be independent, right? Because I sampled 30% of all the Teslas in Memphis. And if my population is Memphis Teslas, and I sampled 30% of them, that's not going to be independent. So it's kind of a thing where you've got to, you got to do it that way. Okay. Let's try a few practice problems, but you're basically done with the lesson. A recent study indicates the probability that flipped coin lands on the same side it started on is about 0.508. For this question only, assume that this probability is exactly correct. Let x equal the number of flips that land on the same side that started on in a series of 8 flips. X is a binomial random variable with n equals 8 and p equals 0.508. A histogram of the probability is shown. Describe the shape. Well, approximately symmetric with a peak at 4. Calculate and interpret the mean. So how would you find the mean? It's binomial, so it'd just be 8 times 0.508, which means if we took, so if many, many sets of 8 flips were observed, we'd expect that about 4.6064 flips to land on the same side as they started on average. It's actually kind of interesting. So it doesn't matter if you're starting with a head or starting with the tails. Kind of interesting. So calculate, interpret the standard deviation of x. Again, you're going to apply that formula, square root of n times p times the complement of p. So it'd be 8 times 0.508 times 0.492 square rooted, all that square rooted. You get that number, which is 1.414. If many sets of 8 flips were observed, the number of flips that land on the same side as they started on would typically vary from the mean by about 1.414 flips. That's your lesson for today.